Hey guys, welcome to Bio 112 Online, your home for biology education. Today's topic, neurons and neuron functioning. This is part 3, action potential. In the last lecture, we talked about resting potential in the Nernst equation. Just as a quick reminder, the Nernst equation is trying to predict the membrane potential, or the charge across the membrane at which ions stop moving. This is a situation in which the membrane is permeable to those ions, but because the charge across the membrane is opposite to the diffusional gradient, then the diffusion balances out with the charge, leading to no net movement. Now we can see this in potassium, where we see a high concentration of potassium inside the cell and a low concentration outside the cell. As those ions move across the membrane, they bring a charge with them. As that charge builds up to about minus 90 millivolts, then you reach a state where net movement across the membrane stops. We can see the same thing happen with sodium ions, in which sodium ions move from outside the cell into the cell, but bring with them a charge. Once that charge reaches positive 62, then you will have no further net movement of ions across the membrane, at least not of sodium. Now this brings us to our concept of resting potential. We have to realize that we have a greater number of leak potassium channels available than the sodium leak channels available. As a result, you have a number that looks very similar to that minus 90 for the Nernst equation for the potassium, but you have just a few of those sodiums still coming through. As a result, you have a resting potential that is somewhere around minus 70. We're going to use minus 70 as our benchmark for today, but realize that in actual neurons at any given time, their resting potentials can be anywhere between minus 60 to minus 80. Now, in order to understand the action potential, we have to bring in two more ion channels. These are going to be the voltage-gated ion channels. You have sodium voltage-gated ion channels and potassium voltage-gated ion channels. As the names suggest, these are channels that only open up and allow ions through when a certain voltage is reached. That certain voltage is referred to as the threshold potential. The threshold potential is the specific membrane potential that, when crossed, causes voltage-gated ion channels to open. For sodium voltage-gated channels, their threshold potential is minus 55 millivolts, which is the point at which they open. For potassium channels, they tend to vary, but tend to open up at some point during the action potential. Now, at this point, we can think about resting potential. Sodium-potassium pump is running. Ions are exchanging. The membrane potential gets to that about minus 70 mark and then stays there, but is not there as a completely stable line for long periods of time. You can have periods of time in which that membrane potential gets more or less polarized. We refer to these departures or changes in the membrane potential in response to a stimulus as graded potentials. These graded potentials come in two main forms. The first of these is depolarization. Depolarization is a change in the membrane potential in response to an influx of positively charged ions in which the membrane becomes less polarized. This typically happens with the influx of things like calcium or sodium. We can contrast that with hyperpolarization. Hyperpolarization is going to be a change in the polarization of the membrane potential in response to an influx of either negatively charged ions or an increased outflux of positively charged ions. The net result of this is that the membrane becomes more polarized than it was at resting potential. Okay, so we have voltage-gated ion channels. We have graded potentials which move us either more or less polarized than the resting potential. Let's put it all together. We're going to start our action potential at resting potential. Recall, while this is going on, sodium-potassium pumps are churning away. Potassium leak channels are allowing potassium out of the cell. This gets us to something close to that Nernst equation value of -90. However, you have those sodium leak channels allowing sodium ions back through across the membrane, which cancels out some of that charge. As a result, we have a membrane potential of about -70 at resting potential. Now, the next step is going to be referred to as the depolarization. That depolarization is going to be an influx of sodium ions. That influx of sodium ions is just enough to bring that resting potential away from the normal and bring the membrane potential closer and closer to that threshold potential of -55. Once it reaches -55, then the sodium voltage gated channels open. Once the sodium voltage gated channels open, then you'll see an influx of sodium into the cell. As that happens, that does one of two things. First of which is it cancels out the existing charge and then makes that membrane so permeable to the sodium that it begins to take on its sodium Nernst equation value, somewhere closer to +55. The next stage is referred to as the falling limb. This happens first because the sodium channels then clog. However, the potassium channels open up, allowing potassium to move from inside the cell to outside the cell. In doing so, they reverse that charge again, bringing it back down to resting potential, and then even further, because you have additional potassium channels available, you end up with a hyperpolarization below resting potential. The final stage is referred to as the refractory period. The refractory period occurs because once the sodium and potassium voltage-gated channels close and become stuck, they can't unstick themselves for some period of time. This is going to be important because it ensures that the action potential only moves in one direction along the axon. So that takes us to our next topic. That next topic is going to be the idea of conduction. Conduction is going to be the process of moving that action potential along the length of the axon, such that once the action potential is initiated at the axon hillock, it can progress and propagate down the axon down to the axon terminus. This process of conduction is actually fueled by the action potential. That's because that signal can go through and move from one portion of the axon to the next. So let's zoom in on the axon and focus in on one segment. We have an action potential take place due to an influx of sodium. As we have that influx of sodium, you then generate the depolarization, the action potential, further influx of sodium, and then that influx of sodium moves to the next zone of the axon, initiating it, followed by the falling limb and refractory period. That signal will move along, like a fuse, the entire length of the axon. For myelinated axons, these are going to be neurons that have glia associated with them, such as Schwann cells in the peripheral nervous system or oligodendrocytes in the central nervous system, in which those glia will go through and put a layer of myelin, a protein, along the length of that axon. When they do that, they do something sort of counterintuitive. That myelin actually shuts down action potentials in any part of the axon which is layered on. As a result, the axon can only actually go through and do an action potential in the locations where the myelin is not found. These portions of the axon in which the myelin is not found are referred to as the nodes of Revnier. In terms of conduction, we refer to this as saltatory conduction, in which you have action potentials skipping from one node of Revnier to the next. It's very similar to conduction, but it has a tendency to travel much faster. So for example, an influx of sodium would result in an action potential, which would then flow to the next node of Revnier, initiating an action potential, flowing to the next and to the next. This skipping motion of the action potentials moves much faster down the axon and also allows that nerve cell, that neuron, to conserve energy because it's only letting smaller amounts of sodium and potassium across the membrane and therefore has to do less work with its sodium-potassium pump. There's another feature that will also allow some neurons to go through and increase the rate at which the signal travels down the axon. And that's specifically if the axon is thicker, then it will speed up the process. So, to sum things up, we have our action potential, which involves sodium moving into an area. Once it moves into that area, it causes an initial depolarization. Once that depolarization reaches the threshold, it will initiate first the influx of sodium through the voltage-gated sodium channels. Those sodium channels will clog, and then will subsequently have an opening of the voltage-gated potassium channels. As they do that, the membrane potential then shoots back below the resting potential into a hyperpolarization. Those potassium voltage-gated channels then clog, and the entire portion of the axon enters a refractory period in which no further movement of ions can take place. That action potential can then proliferate its way down the axon by letting the sodiums that just came in from one area seed the action potential through a depolarization in the next adjacent location. And that can continue along the length of the axon in one direction because that refractory period will prevent it from moving in the opposite direction. In the case of myelinated axons, you instead have a process called saltatory conduction, in which those action potentials jump from node of Revnier to node of Revnier, leading to an increased rate of transport for that signal. Once that signal does reach the axon terminus, it will then stimulate the release of neurotransmitters across the synapse, which will then transmit the signal for the next cell. But that is the topic of our next lecture. So until then, stay safe, stay healthy, and I'll see you later.